Hello and welcome to today's topic on data evaluation at the advanced level. We do also have a notebook on basic level of data evaluation, so you're also welcome to have a look at that, or maybe you already have, and then this notebook will provide a little more detail than the basic notebook has. So I will equally, if you have seen other tutorial videos, I will equally walk through this notebook, explain some theoretical input, and then click through the practical aspects of this notebook and explain what it is that we're doing as we go through this notebook. So welcome. This is the topic of data evaluation, and more specifically, we will calculate automatic evaluation metrics. So these are metrics that we can use to calculate quality scores for machine translations. And we will look at two string matching metrics called BLEU and TER. And we will also look at two embedding-based metrics called BERTScore and COMET. There are other variations and in general other metrics, but these are four very common ones that we will be covering in this notebook as well. So in case you've looked at the other notebook or video, you will know already that these scores are mostly calculated by comparing a machine translation sentence, which is considered a hypothesis, to a human translated sentence, which is considered the reference. So this human translated sentence is considered the gold standard, kind of what we want to achieve, because these are frequently translated by professional human translators. So this is considered the gold standard, the reference, and then the machine translation sentence that we have in comparison is the hypothesis. So these are the two sentences that we compare, and usually we aim to have the hypothesis to be as close as possible to the human reference. And for COMET, the last score that we will cover in this notebook, we will also include the source sentence in the calculation. We will go into more detail later on. So first of all, as always, we will upgrade our pip, so you can just always simply run the cells in this notebook by clicking these run buttons. And once again, some of these cells will take a little longer to run, and some will be run quite quickly. So sometimes you just have to be a little patient. Sometimes it also depends on how well your connection is at that point. And there we can see that it is loading and that we are getting our output. And we have successfully installed the latest pip. So now we can move on, and the first topic will be our string-based metrics, so BLEU and TER. And important to know here is that string-based metrics compare the actual strings of the sentences, so the actual words. And there is more information on this in a companion notebook on the topic of string matching. So you can have a look at this notebook that I've also covered briefly in the basic level video, because here basic concepts such as precision recall and n-grams are described in more detail. So you're welcome to have a look at that notebook that gives a brief overview of these basic concepts. And we will move on to the first string-based metric called BLEU, which was originally proposed by Papineni et al. Already in 2002. And yet it is one of the metrics that is frequently used in research. Nowadays also often a different version of it called sacreBLEU, which is a standardized method for BLEU. So this is also the one that we will be using here. And just to give a little overview of how BLEU is calculated. So for this, the concepts of precision recall and n-gram are quite relevant to understand. And this is the actual formula, how BLEU is calculated. And I won't describe exactly what all of these aspects mean, because you can read that here in this notebook as well. But important to know is that the exact strings, so the exact words are compared in the hypothesis sentence and in the reference sentence. And with BLEU is a similarity measure, so it measures how close these two sentences are to each other, how similar these sentences are. And the higher the BLEU score, the more similar these sentences are considered to be. So the higher the BLEU score, the higher the quality of the sentence. So we want to achieve a high BLEU score. And exactly, so this is how the BLEU score is calculated. And without going into too much detail, you can see here that these are n-gram calculations. So they compare how many n-grams are the same between the hypothesis and the reference sentence. And by calculating all of the comparisons, the n-gram comparisons, the BLEU, this aspect of the BLEU score, BLEU metric calculation can be calculated. And naturally, the more n-grams that compare, the higher our value will be. And here we will also then calculate the geometric mean of the n-gram values. And without going into more detail, you can have a read through this of how exactly we would calculate these n-grams. But also what is important to know, for example, is that this aspect, this part of the formula is called the brevity penalty. And it actually penalizes a machine-translated hypothesis sentence if it is shorter than the reference sentence, because then we are expecting that maybe there has been something forgotten. So maybe the machine translation system forgot to translate certain words. So we do not want the hypotheses for BLEU score. We do not want the hypothesis to be shorter than the reference. Otherwise, it gets penalized. If it is of equal length or if it is longer than the reference sentence, then it does not get it is not penalized. So this is sort of what the brevity penalty calculates here and checks whether the sentence will be penalized or not. So after explaining a little bit about the exact calculation of BLEU score, we can actually go ahead and calculate our own examples. So as I mentioned, we are working with the sacreBLEU implementation. So once again, you can just run the cell and load the sacreBLEU function here, installing it. And then let's have a look at a short example. So we are defining our hypothesis to be, I drove the automobile to the gasoline station. And our reference is, I drove the car to the gas station. So if you have seen the video at the basic level, you will see that these are the same sentences that we've used there. And we can calculate the BLEU score for these two sentences. So what the score does is it compare the exact strings, so the exact words in these sentences. All right, so as you can see, we get a BLEU score of 27.05. And what we did not cover in the basic level notebook is sort of how exactly this is calculated. So first of all, important to know is that the BLEU scores range from 0 to 100, with 100 being the highest possible score that you can get. So 27 is below average, but in real life MT quality evaluation scenarios, BLEU scores are rarely as high as 100. They start becoming competitive from around 20 upwards. So it is always important to kind of know in which frame the scores are considered. So if you look at a value and think, oh, it's very low in comparison to 100, it might not be as low if you look at competitive values out there that are frequently not 100 either. So what we can see here, as well as some more information, so we can see we get a brevity penalty of 1, so it is not penalized in this scenario. And that is the case because we can see that the hypothesis and the reference sentences both are of equal length. So they both have 8 words. So there's no penalization here. And then here, these values are sort of the n-gram comparisons. So we can compare how many n-grams overlap. So the first one calculates how many 1 grams overlap. The second one calculates how many 2 grams overlap. And the third one, how many 3 grams overlap. And the last one, how many 4 grams overlap. You could also calculate more than that, so 5 grams, 6 grams, but the average BLEU score is automatically calculated with a maximum of 4 grams. And the comparison, you could, for example, see 1 grams, you see, okay, the I and the I compare, drove and drove, the and the, but then at automobile and car, this is already not a comparison, so this doesn't count. Then to and to, the, but then gasoline and gas don't overlap, so they don't count as 1 grams, and then station and station count again. So that is how the 1 grams are compared, so one word at a time. 2 grams are then a comparison of I drove, or drove the, so those compare. But then, for example, the automobile and the car do not compare. And automobile 2 and car 2 also don't compare. But then to the compare. But then once again, the gasoline and the gas, or gasoline station and gas station, already don't compare. And then we can see I drove the is a 3 gram that compares with I drove the down here. But then drove the automobile or drove the car already don't compare. So this is how the n grams are compared. And for a 4 gram, for example, you would look at I drove the automobile and I drove the car, which already also don't compare. So this is how the n grams are calculated for the 1 gram, 2 gram, 3 gram, and 4 grams. And you might be surprised that there are no 4 grams that actually overlap in the sentence, but we still get a value of 10. And that is due to the fact that we can't have a value of 0, because otherwise the entire BLEU score would be 0, and it would be a bit harsh to give this comparison, this BLEU score, a value of 0, considering that there are a lot of similarities in the sentence. So in order to avoid having a value of 0, there's a so-called smoothing function applied that assigns a small value to, in this case. And we won't go into more detail here of the smoothing function, but you can read this link below here if you want to learn more about it. But this is just sort of adding a little value to prevent the fact that we would reach an overall score of 0. All right, so now that we have calculated an example value of BLEU for the sentences we have provided here, we can try the same for our own example. So here we can input our own hypothesis and our own reference sentence. So let's take a look at this. We can just run the cell here, and then we can type in our hypothesis. Let's say I rode my bike to the beach because the sun was shining. Full stop, and then you click enter. And then we can say I cycled to the beach because the sun was out. Enter. So now we have defined our machine translated sentence and our human translated sentence, and we can run this cell here to calculate a BLEU score. And we can see that we get a BLEU score of 50, so that's actually quite high. And we see that the hypothesis length is 13 and the reference length is 11. So we do not have a brevity penalty here applied, because the hypothesis length is longer than the reference sentence. And once again, we can break down the exact calculation of BLEU in the comparisons. We can compare 1 grams, and we can do that by looking at how many 1 grams compare. So I and I, road and cycle don't compare. My and to, bike and to, in this case also don't compare. But then to and to, the, beach, because, and so on. And then we can do the same with 2 grams. We can look at how many 2 grams compare, like the beach, the sun. So those kinds of comparisons. We can look at 3 gram comparisons, for example, to the beach, or because the sun. So those are 3 grams that overlap. And let's just have a look if there's also 4 gram overlapping here. And we can see that we actually have a few 4 grams overlapping here as well. We have to the beach because, and we have the beach because the, and beach because the sun, and because the sun was. So we can actually see that we have quite a few 4 grams overlapping here. And even though we have less 1 gram and 2 grams overlapping than above, we do have quite a few foregrounds overlapping, which is probably why we have a noticeably higher BLEU score here than we did above for the example. So now we can also look at another string-based string matching metric called TER. So TER is also a string matching metric similar to BLEU, but whereas BLEU calculates the similarity of the hypothesis and the reference sentence, TER actually compares and calculates the dissimilarity, so how dissimilar the sentences are. And TER is calculated by the following formula here. And the difference also here is that the lower the TER value, the higher the quality. So opposite to BLEU, we actually want a very low value of TER, because TER calculates and adds the editing operations that would be required to transform a machine-translated hypothesis into a human reference. So it looks at, for example, substitution, so substituting a word for another. It also looks at insertions, when a word is inserted or deleted, and add moving an element to a word to another position, so shifting. And all these will be summed up and divided by the length of the reference sentence. And we are looking at TER, sort of the original TER by Snover et al. In 2006. That calculates this on the basis of words. There is also a character which calculates on the basis of characters, actually. So you can have a look at that here. But that is pretty much what we need to know here for TER and how it is calculated. So we can go ahead and do that. Once again, we have to actually install TER here. So we just run the cell and download the packages needed. And once that's done, we can look at our example again. So once again, we have the same example as we have above. I drove the automobile to the gasoline station and I drove the car to the gasoline station. And we can see here we get a value of 0.25, which is, so this is a value that is calculated between 0 and 1. And we can see that this value is relatively good. So this is closer to 0 as it is to 1. So that's already a good sign. And we can see here that we also only have to do 2 substitutions, or we would have to do 2 substitutions. So the only thing we would have to do is substitute automobile by car and gasoline by gas. So the way this would be calculated then is to say 2, because we have 2 substitutions, divided by the length of the reference sentence, which is 8. So 2 divided by 8. And that gives us the value of 0.25. And it is interesting to see that sort of we get a better value for TER for the same sentences that we do in comparison to the BLEU score value, which in comparison was only 27 out of 100. So this shows us that for the same hypothesis in comparison to a reference sentence, we get 2 very different scores depending on the metric that we use to calculate these scores, showing us that it is always really important to situate your scores within what it means, by looking at, okay, how are these metrics valued, but also by maybe calculating different metrics to receive different scores and compare those. So, because for example, if you would look at the BLEU score above of 27, you would think, okay, it's quite a bad quality, but then you look at this TER score of 0.25 and you realize that the quality is not too bad after all. So it is always good to test different metrics and calculate different scores for your machine translations before reaching a conclusion. All right, now we can go on to calculating our own example once again. I will go up to copy the sentences that we've used before. So I will go back and copy my machine translated hypothesis sentence. And we can do so by running the cell here again, and then I will copy my sentence here, enter, and then I quickly have to go up to copy the reference sentence. And I will paste it here, enter. Right, now we've once again defined our sentences and we can run the cell to calculate TER. And here we see that we get a value of 0.36. So this value is higher than the one we received above. And by looking at the sentences, even without going into too much detail now, we can already see that, sort of understand why we get a higher value here, so a lower quality, because we would have to do more in order to get from the hypothesis to the reference. For example, we would have to change rode my bike and cycled, so there would already be maybe 2 deletions and 1 substitution here, and then there would be another substitution here from shining to out, so that would already be 1, 2, 3, 4 edits, if I'm not mistaken, and now we have a reference length of about 10, so that is why we get the tear score that we get. There's more sort of work that we would need to put in here in order to get from the hypothesis sentence to the reference sentence. And because of this more work, we get a higher tear score, meaning a lower quality of the sentence. But as you can see above, in this case, if you compare the BLEU score and the tear score, we got a higher BLEU score of 50, which is actually quite competitive. So once again, it is always important to compare different scores from different metrics and not to just take one value as face value and as the right answer. All right, so now we've covered string matching metrics, and we will move on to embedding-based metrics. So for this, we will talk about 2 metrics, one called BERTScore and one called COMET. And we will look at a bit more information on what this means and how these are calculated. So in comparison to the string matching ones above, as the name suggests, and as I had mentioned before, they compare exact strings of the words. So they will compare, for example, beach with beach and realize, okay, it's the exact string, the exact same word, so that would be correct. Or they would compare car and automobile and see that it is not the same word. So they would consider this as a wrong word, as a wrong translation. Whereas these embedding-based metrics, they look at word embeddings, and what word embeddings do is that they look at the similarity, sort of. They can understand the meaning of the words. So what they exactly do is that they look on the semantic similarity between a hypothesis and a reference based on their proximity in vector space. And there's more information on this in this companion notebook that you can click on. The first embedding-based metric that we will look at is BERTScore. So BERTScore is a semantic, or calculates the semantic similarity in vector space. It was proposed by Zhang et al. In 2019, so not that long ago. And the difference to the word embeddings that we looked at in the companion notebook is that those are sort of standard or normal word embeddings. But what BERTScore actually calculates are contextual word embeddings. So they can actually look at the context that the word embedding is placed in. So it is actually really smart, because then depending on the sense in which this word embedding, this word sort of is used, it can really sort of analyze that. And you can see in the example below here, the sentence where it says the weather is cold today or it is freezing today, how the words are analyzed. And you can see that it and the have a semi-similar meaning in this case. And the fact, for example, today and today obviously have a very close correlation because it's the same word. But then if you look at, for example, cold and freezing, that they also have a very close correlation because they mean relatively similar, they have a very relative similar meaning, and also is and is has a very close correlation. So this is also an interesting image to show, to express how these word embeddings are sort of analyzed also in its context, and how then BERTScore is calculated, because this is sort of what BERTScore bases its calculation on. and then it matches words in the hypothesis to words in the reference sentences based on the cosine similarity of their word vectors. So this is a very quite clever form of calculating the quality of a machine translation. And we can go into a little bit more detail here, how this works. So kind of to compare it with what we can see here, BERT actually tokenizes the hypothesis. Tokenization is a topic that we also discuss in our data planning and collection learning resource, in case you're interested to hear more about it, where a word is split into subwords. So BERT tokenizes the hypothesis sentence into a candidate and into a reference sentence, and then it converts the individual tokens into contextual word embeddings. So you can see the part of contextual embedding above. Then it calculates a cosine similarity between each word in the embedding, both in the hypothesis and of each embedding in the reference. This is also explained more closely in the companion notebook. And here the step is the one where it says pairwise cosine similarity. And then we have the similarity matrix, which we can see here as maximum similarity that I just talked through in a bit more detail, where we match the words that are the most similar. And these words get similarity scores. And then based on the matching of the contextual embeddings, according to the cosine similarity that's calculated here, BERTScore then calculates a value for recall, for precision, and then combines these two values to calculate an F-measure score. So these are also discussed, these concepts are also discussed more in the string matching companion notebook, where we discuss recall, precision, F-measure, but here they are BERTScore specific. And then this final score, the final BERTScore would be this F-measure score, and we will show that in the example below. So that is what we will do now. We will go here, and once again, we will install what we need to be able to calculate BERTScore. So we will install the packages. And in comparison to string matching metrics, these embedding-based metrics, because of their complexity, because of how a little more complex they are calculated, installing the packages will take a little longer than installing the ones above, so you just have to be a little patient, but you can see it's already installed. And then we can go down here and once again look at our example. We're using the same example as above to calculate our BERTScore. We can define our sentences here, and then we can run the cell to calculate our BERTScore, which takes a little longer than above. And we can see here that the sentences that we're working with are in English, which is why here we are referring our language to be English. So we're using the English language code. If you are using sentences that are German or Spanish or any other language, you would have to change this language code here. And for example, for German, you would have to refer to DE, or for Spanish, you would have to refer to ES. And most languages are, BERTScore can deal with most languages, but you can also look at that in the BERTScore documentation just to make sure which language score you can use. But just as a reference, that here we're using English. And you can see below now that we have calculated a BERTScore for recall, for precision, and then the combined one for F-measure. So this combined score of 0.86 is our BERTScore. And we can see once again that we get a value that lies between 0 and 1. So BERTScore is calculated between 0 and 1, and we get them as tensors. And we can see that the value of 0.86 is relatively high. So this is a relatively high score. And you can see that by looking at the sentences that the meaning of the sentences is pretty much the same. So apart from the fact that we're using automobile instead of car or gasoline instead of gas, the sentence conveys the same meaning. And in comparison to BLEU or tear above, BERTScore can actually analyze this meaning and see that these sentences are more similar, because it is able to compare the word embeddings of automobile and car and realize that they are more similar than the actual string comparison, which shows that they're opposite, like completely different words. So we can see that from BERTScore, by calculating the semantic similarity also in vector space, we can see that the meaning of the sentences is relatively close. So we get a relatively high value here. And as we defined above in our sort of theoretical definition, we can actually see this in practice, where we can look at the similarity matrix of our two sentences. So here we have our hypothesis sentence: I drove the automobile to the gasoline station, and then our reference: I drove the car to the gas station. And always this line in the middle here, we can see that they are rated quite highly, where obviously we have very high values for station, because it's the same word that is used, and for the or I, because naturally those are the same, and drove, the same words. And then we can see that this is the one for automobile and car, and we still get relatively high values, so we still get 0.9. And the same for gas and gasoline, we still get relatively high values. So this shows that this metric actually understands that the same meaning is being conveyed, even though different words are being used. So this is very interesting, also to have a look at the similarity matrix and to understand how BERTScore is calculated. And as we have done above, we can once again calculate our own BERTScore with our own sentences. So I will go up to copy the same sentences that we've used above. So let me copy the hypothesis sentence. And then we have to run this here, and then we click enter. And then I will copy also the reference sentence that we've used above here. I will copy it here. And I will enter this here and then click enter. So once again, we have to find our hypothesis and reference sentence, and we can run the cell here to calculate the BERTScore. And once again, remember, now we're also using English sentences, so this is correct. Just in case you use your own sentences and you use it with a different language, remember to change the language code. And then we can see down here again, we have a BERTScore for recall, precision, and F measure, with F measure being the final score that we have, and we receive it as 0.829. So once again, it's relatively high. And we can run the cell below here to get our own similarity matrix, or a similarity matrix of our own examples. And also we have to just be patient for a little while, because here we can analyze it a bit more closely. So we can see that things like the sun, was, because, and beach, that these receive relatively high comparison values because they are the same words that are being used here. But then here, where we have rode my bike, or in the other sense we have cycled, it's scored a little lower. So here we can see that, you know, where the words are the exact same or very similar meanings, that they get really high scores, and here where we formulate it a bit differently, we get a little lower score. So once again, that is probably what affects the fact that we don't get a really high score. But yet again, it is a very similar meaning that these two sentences convey. So once again, we do get a relatively good value for BERTScore. Especially these sentences that we compare here that are very similar in meaning with yield us quite high values for all these metrics that we're calculating here. If we're comparing machine translations to human references, often they can vary very much. So you might not always get values as high as the ones that we're calculating here. All right. The next embedding-based metric that we will look at, and also the last one in this notebook, is COMET. So COMET, just as BERTScore, COMET is also a semantic similarity, but it additionally is trained on human quality judgments. And COMET was proposed only a few years ago, in 2020, by Ray et al. And once again, it is also an embedding-based metric, so it also looks at the embedding-based similarity of the reference and the hypothesis sentences. But different to the previous metrics that we've discussed in this notebook, COMET also looks at the source sentence So it looks at the hypothesis, the reference, and the original source, which is an interesting addition here, which also seems to make a lot of sense. So these three sentences are fed into a pre-trained cross-lingual encoder, and it embeds them in a multilingual vector space. So BERTScore was working with a monolingual vector space, so it was only comparing the hypothesis and the reference sentences, which are always of the same language. But here, these sentences are encoded in a multilingual vector space. So this means that not only words from the same language are sort of clustering together. So if they mean the same, they would be clustered together, but also words from different language with the same meaning are clustered together. So for BERTScore, we would only have one language. So for English, for example, similar words with similar meanings would cluster together. But here also different languages can cluster together if they have the same meanings, the words. And this means that we can also use the source sentence. So for example, if we have the source sentence that is German, but then we have the hypothesis and the reference that are English, COMET will understand if they have the same meaning because of this multilingual vector space. So we can have a look at this in a little more detail. All right, on the left we have the estimator model, or also called regression metric, where we can see that the model takes as an input the hypothesis, the reference, and the source sentence. And then these sentences, these three sentences, are then, the model takes their contextualized word embeddings from the multilingual vector space, and then these embeddings are pooled into one single word vector. So these, the vectors of the three sentences are concatenated into a single vector, and this one vector is then fed into this feed-forward regressor, which then calculates the final quality score. So the COMET estimator model, the one on the left, is trained on human error annotations. So this is where we also have the human quality judgment. The error annotations based on the multidimensional quality metrics framework, the MQM framework. And we get a calculation, so there's a ranking, human ranking of MT outputs on a 100-point ranking scale, considered the direct assessment. So now it gets a little more complicated. In the middle we have the translation ranking model, or also considered ranking metric. And here you can see once again we have the source as an input and the reference. But now we take two hypotheses. So let's say we have two machine translations, one being considered or ranked better according to the direct assessment. So that would be the positive one. And one would be considered worse. So that would be the negative one. And the same as in the first model, now we have these four sentences that are inputted into this model. And from these sentences, we now obtain also contextualized word embeddings. And these are also pooled into sentence vectors. And then we get, it gets a little bit more complicated. So now the distance between the source vector reference, the source and the reference in comparison to the vector of the hypothesis increased. So if the distance increased, it means that there's a lower semantic similarity. So now they're further away from each other. So this is for the worse hypothesis, you know. They say, okay, this is worse. This is further away from each other, meaning-wise. And the distance between the source reference and the better hypothesis is decreased. The distance is decreased, so they're being put closer to each other, meaning that they are semantically more similar to each other. So this ranks the positive hypothesis as better, and it ranks the negative hypothesis as worse. And then for the calculation, we use the source, reference, and hypothesis to then calculate the harmonic mean, so a mean of the Euclidean distance, so the distance between the hypothesis and the source in comparison to the Euclidean distance, so the distance in vector space between the hypothesis and the reference. So this is all very detailed and no need to necessarily understand it all, but that is what these models do. And then on the right-hand side, we have a reference-free COMET or referenceless metric, which is also really interesting, where now you can see that we only input 2 sentences, so we do not have a reference. So imagine you do not have a professional human reference to compare your output to. So we only have the machine translated hypothesis and the source sentence. And the same as the other models, these are converted into contextual word embeddings. These sentences are read as contextual word embeddings and converted into sentence vectors and then combined into a single vector. But important to know the difference here is that we're not working with the reference sentences, so we're not evaluating the quality of the machine translation, we're rather estimating the quality, because we can't say for sure how good or how bad the translation is, but we can give an estimate based on the source sentence how good or how bad the hypothesis might be. So an overview of all these models together with information on how to load them, so how to use them, can be found in the official COMET GitHub repository. So now that we've explained this theory, which is, you know, a little intense, I hope, it was sort of conveyed understandably enough, we will actually go on to just test calculating our own COMET scores as we have done for the metrics above. So once again, we have to install the according package. And once again, this is also an embedding-based metric, so the installation might take a little longer than above. And one thing you will notice here is that we might have to restart our runtime, but we will do that in just one click. So that will be really easy, and you will see that in a moment. So you can see here we get a warning that we have to restart the runtime. So we can just click here, and it asks you, are you sure you want to restart the runtime? You can just click yes. And then what we've run before has been sort of deleted, but we don't need to have the BLEU packages and all the other ones installed again. The only thing we can do again is upgrade pip, because it's always good to work with the latest version of pip that we have. So we just let that load for a little while. Perfect, then we can go back down, we can skip all the other steps, we can go back to our COMET step and reload this. So now we will install COMET again, and this time it should work. Perfect, now we don't have to restart our runtime, so we can move on. So the first version that we're using is that we're using Cometinho, which is a lightweight model of COMET that was only proposed in 2022. So this is a lightweight version of the original COMET. So it offers basically the same performance as COMET, which is a much bigger model, but it does so at a much faster speed. So it loads a lot faster. So to use that, we have to load COMET, the Cometinho model. So we're using the EMT 2022 Cometinho DAT model, which we have taken from the documentation that we referred to above. So once again, you just have to load this for a little moment. This will take a little longer. Right, perfect. Now that it's loaded, we can go and calculate an example. So now we have different sentences here because we also need a source sentence. So now we have a source sentence that is English, and it says, if you do not agree to these conditions, do not use this website. And we have a machine-translated hypothesis. Wenn Sie mit diesen Bedingungen nicht einverstanden sind, benutzen Sie diese Webseite nicht. And we have a reference, a human reference. Wenn Sie mit diesen Bedingungen nicht einverstanden sind, sehen Sie von einer Nutzung dieser Webseite ab. So we can just run this cell to calculate the Cometinho score. And you can see it down here. The Cometinho score we get is 0.68. And above that, you can also see that we get a segment score, which is also 0.68. So the segment score is calculated per sentence. So if we have one sentence, as we have here, then we get one segment score. If we have two sentences, we would get two segment scores. and then get an average COMET score. We will show that in the calculation below. But what you can always focus on is the actual COMET score, so at the bottom. And the thing with COMET is, in comparison to BERTScore or other scores, other metrics, where there's a clear sort of line and a clear comparison as to what is considered to be a good and what is considered to be a bad score, does not really exist for COMET or COMET. So it is always best to compare different hypotheses or different calculations of COMET to see, okay, which is the better version, which is the better hypothesis, which is the better machine translation in comparison to other machine translations that we've had. For example, if you are training your NMT model and then you have a machine translations in the end, and then you are adapting something to the model because maybe you want to improve the quality, then you recalculate it and you get new machine translations, and then you compare COMET or COMET scores of these different machine translations. Based on that comparison, you can see, okay, which ones are better, so which scores are better. It does seem to be that the higher scores are also higher quality, and we can see that here, where now we have two sentences. So now we're using multiple sentences. We have the same as above, but we also have, please read these conditions, they are important, as the source. And as a machine translated hypothesis, we have, bitte lesen Sie diese Bedingungen, sie sind wichtig. And the reference, bitte lesen Sie diese Bedingungen durch, sie sind wichtig. So we can see from above that these sentences now get the same score as we'd had above, 0.68, but the sentences below get a COMET score of 0.99. So this is a much higher score, and we can see that these two sentences are a lot more similar as well. The only difference is the word durch. So we can see, okay, this one gets a relatively high score because also the sentences are very similar. It seems that this is the better score that we would get here. And the average score for COMET that we get for both sentences is 0.83 or 84. So it's a bit higher than the score we received above. And that is how you that is how you can calculate COMET scores, also for multiple sentences, and then compare the meaning of the scores. What we can also test now is actually the reference-free COMET model. So without using a reference, and I actually find this really interesting. So for this one, we will load the WMT21 COMET QE MQM model. So before we used the EAMT 2022 COMET model, now we're using the reference-free model. And once again, this will load a little bit. All right, so in comparison to the one above, we can see where COMET was a lightweight model. This one took a lot longer to load, almost 3 minutes, so we can see the model here is a bit more hefty. So what we can do now, imagine we have two different machine translation models or two different machine translation systems that we're using, and we want to compare their translations. So we can calculate a quality estimation score based on just the source and the hypothesis. So let's say we have a source which says the same again. If you do not agree to these conditions, do not use this website. And we have one hypothesis. Wenn Sie mit diesen Bedingungen nicht einverstanden sind, benutzen Sie diese Webseite nicht. And then we have a second hypothesis, which says, ich bin froh, wenn dieses Notebook endlich zu Ende ist. So these are two very different meanings, very different sentences. Don't worry if you don't speak German, but these sentences, so this is a translation of the sentence, and this is a completely different sentence. So we can run this cell to calculate a quality estimation score. And as above, we once again get a segment score, and which is 1 because we have one sentence, and the COMET score, and the COMET quality estimation score, sorry. And we get a value of 0.158, so 1.6. And then let's run the cell below with a completely different sentence. and we get a value of 0.11. So once again, it's a little difficult to interpret a value by itself, and these values are rather low in general, and these are estimated scores and not a evaluation. But we can see here that up here, where this is an actual translation, the hypothesis is an actual translation of the source sentence, at least the value that we get is higher than the value down here, which is much lower, where the hypothesis sentence has nothing really to do with the first sentence. So this is also still being worked on a lot, the aspect of quality estimation, because it is much harder to analyze sentences without having access to the reference sentence, but it is a very interesting field of research. So congratulations, because we have run through this entire notebook and we have explained in a lot more detail the theoretical concepts of BLEU, TER, BERTScore, and COMET, and we have calculated values for each of these and explained these values in hopefully much more detail than at the basic level. What you can now do is you can also have a look at this companion notebook on quality valuation at document level, because what we did here is that we calculated always these metrics only at sentence level, but you can also calculate average scores for entire documents, which is very helpful to do if you are comparing your machine translations, which might often be a document or a paragraph in comparison to merely a sentence. So you're welcome to have a look at this companion notebook on document level, for which we also have a tutorial and accompanying video. Furthermore, you can also train your own NMT model with data and then use that model to create a machine translation and calculate these four metrics. So have a lot of fun if you want to try that, and otherwise, congratulations on completing this notebook.